if you have any questions or concerns on those. All right, so first three answers, we want 3, 2, and 4. How'd you guys do there? Perfect. All right, next, to list out your sample space, you can do this in a variety of ways. You can do like a tree diagram if you wanted, or I just wrote out all the ordered pairs just so that I didn't forget anything. And my bottom one too, I just need to change that answer because you are out of 16 outcomes altogether. So that would be 0.1875 for that solution. And the blood collection agency that tests 50 blood samples, so you want the probability of type B blood is 7 out of 50. I don't know if that's accurate or not either. Good on the front? Okay. Next page, because again, you did have a lot. Remember that empirical probability is like an experimental probability. So it's not what happens in theory, it's what happens if you actually survey people. And you've got a table here that you had to figure out too. So you're just going to add and subtract to get all of those totals. Everyone's using great proper probability notation. So please keep continuing to do that because today we extend these to your formulas. And marginal distributions are shown on the side there. And then all your probabilities below. There was one of these that I had something, a digit off. I think it's this one. Was this like 0.224? 274, thank you. I knew it was somewhere, but it wouldn't save on me. 0.274, thank you. All right, any issues on any of those, guys? Yes. So probability by definition is always a number less than 1. So yes, the larger number does always go on the bottom. Yep, and it's always after my such that. Yes. And some of that notation is meant to kind of help you get things set up as well. Excellent question. I'm going to keep rolling on to the next page here. So you have 40% of students involved in one or more activities, and then you have a hypothetical 1,000 table. It just means your table's out of 1,000. And again, it allows us the ability to not work with little teeny decimals. So you'll do another one of those again today. Any problems on the two-way table? They were somewhere. Right here. Yes, you just move your decimal over. Yep, no problem. Just move your decimal. So that's where the 232 came from. Same thing as the 580. Yep, and then add and subtract to kind of keep building things. Notation at the bottom here. Male does not participate. A lot of 40% answers, right? Yeah, a ton of 40% answers. And then I think this one had one more page, correct? Yes. And again, as I hope you saw with these, weren't a lot of them really fast? Yeah, so that's why it seems like your packet's really thick, but again, I'm not trying to overload you on, extra work. I just know that these go super quick. So again, more 40% answers there. Again, you can leave those as decimals though. Explanations, again, just make sure you have something that's specific based on math. And again, if you take stats in the future, you are going to be required to write nice complete sentences. So if you want to practice that, you're more than welcome to. I think that's it on that one. And then you had problem set number 2, and these were your tests for independence. And there are a variety of ways that you can complete these, but it's going to yield the same answer. Don't go changing something if you have it. Again, if it gave you the same answer as me. So we want the probability that a certain student has asthma and the probability of asthma given the condition they are a smoker. Those are not equal probabilities, thus those are not independent events. And what you're going to do today is a test for independence without a two-way table. So we have another formula that we utilize instead. Hypothetical 1,000 table. And again, I put up 2 ways that you can show a test for independence here, but that's not an exhaustive list. So you could do a couple other pairings up as well. But either way you do it, those are all going to come back as independent. So again, you don't have to have both. or you might even have a third one that I didn't fit up there. Okay, but I need to see the math that goes behind those. So we need to see the two fractions set up. I think I gave you another test for independence on the back here. And again, you can choose for this one. So it was supposed to be kind of open-ended, but whatever music genre you picked, those should not have been equal. Okay, so your setups can definitely vary on those. And then the last, this one's a little bit more straightforward. You probably just want the two values there, and those were not equal to each other, also not independent. So not independent events. All right, how are we feeling on those overall? Pretty good? Because it means they have no impact on each other. Yep. Which is kind of what we get into today too. We're going to talk about a disjoint relationship. All right, so we are over to day 3. So moving right along here. So let's talk about some notation too. And again, I'm not sure what you've seen in the past in regards to probability. So we'll just kind of make sure. I'm going to have you add some formulas here. So in the past, have you guys seen this notation? It's okay if you say no. Yes, no? This is what we call an intersection symbol, and it stands for and. So that represents the probability of events A and B occurring. We also have another notational symbol we use for probability, and that is what we call a union. So do this then. So a union, see how the union has a U in it? So it just flips. And that stands for or. Okay, so we use those notational symbols a lot with probability just to kind of make things a little bit shorter to write out. So we're going to talk about what's called a disjoint events, also referred to as mutually exclusive. And this means that the events have no outcomes in common. Okay, so their sample spaces are entirely different. So suppose, for instance, that you roll a die. So if you roll a die, my sample space is going to be, and this is always assumed to be a standard die, 1, 2, 3, 4, 5, and 6. So you have 2 events. Event A says you're going to roll an even number. So how many even numbers do I have currently up here? Yes, 3. And they would be 2, 4, and 6. Then event B is the probability that I am going to roll an odd number. Were any of those the same? No. So 1, and then 3, and then 5. So what we say is that these are mutually exclusive events because they have no shared outcomes. They're all different. So what that means is that the probability of them occurring together is impossible. So that's why it's equal to 0. So here's a counter example. So suppose you have this event, you're going to roll an even number and you're going to roll a prime number. Okay, so first let me step back. You guys know what prime numbers are? Yes, so what is the first prime number? No, 2. Yeah, that's why I'm asking, because sometimes we accidentally assume that you remember things like that, and probability does pull back from some past knowledge. 1's not a prime number because it's only divisible by 1. So your first prime number is actually 2. So primes are 2, 3, and 5 on a die. Okay? Just so you don't make that mistake in the future. 1 is not a prime number. So I want you to write that because it's, again, a common mistake. So 1 is not prime. So these events, the probability of rolling an even number and the probability of rolling a prime number, are not mutually exclusive because they share 2 as an outcome. Okay? So using the example from above, we want to list out the sample space. Okay, that's quick and easy. We already did that. Sample space of a die is 1, 2, 3, 4, 5, and 6. All right, next. The probability that event B will occur. What was event B? I forgot. Odd number, thank you. So we'll say probability of odd. The probability of odd is equal to, how many odds were up there? 3, right? Yep, so 3 over 6 equal to 0.5. Now we're going to introduce some notation. So next what you want is the probability the event A or C will occur. So this is what we call a union. So this is a union, and what you're going to do is combine all of your outcomes. So we are going to combine them. So the probability for event A, I need that list down here somewhere again. So A must have been evens, correct? Thank you, 2, 4, 6. And then sample space for C was my primes, which were 2, 3, and 5. We don't need to obviously list the 2 twice. So the probability of this occurring, if I can combine them together, is going to be the numbers 2, 3, 4, 5, and 6. How many is that all together? We have just 5 of them out of a total of 6. Somebody get that as a decimal, please. Say it again. Thank you, 0.83. That's what I thought. Okay, so that's how you do a union, is you combine them together and you don't write the repetition. Now we're going to go the opposite direction. We're going to do an and statement. So what do you think an and, which is an intersection, means? Only, yep, excellent. Only the overlap. Good. So this is the opposite, or the shared outcome. What did they share here? Yeah, just the 2. Yep. So this would just be the 2. So this would just be 1 over 6, which is, yep, thank you, 0.17. I think it's 0.16 repeating. Okay. So what we're going to do today is we're going to start working with some formal probability rules. So you have down here your addition rule, and this is if they're disjoints, so they have nothing in common. So the probability of A or B, and I want you to write this out with proper notation, please. So A or B is A union B, and that is equal to the probability of A, and then plus the probability of B. And again, this is going to be for your case that is disjoint and has no shared outcomes. Okay. We also have a union rule if you do have shared outcomes. So this is the rule when they are not disjoint, which you're actually going to see most often. And here's how this goes. And again, if you were sitting for a Regents exam, you would have to memorize this. Okay. So the probability of A or B occurring is equal to the probability of event A plus the probability of event B minus the overlap of probability of A and B. So think of this as like the overlap or the shared. We also have another test for independence that we're going to do for this case as well today. So what you're going to show, I'm going to say rule for independence. And again, this is the one that's most helpful when you don't have a two-way table anymore. Is you are now going to show instead that the probability of A times the probability of B must be equal to the probability of A and B occurring. Okay, and these two are your main two formulas that we're going to use today. Okay, we can obviously kind of flip-flop them too. So here's your first example on the back. And anytime you have a big paragraph, such as this, I like to start pulling the math kind of off to the side so you can kind of isolate it. So it says, students chosen at random. The probability that the student selects math as the favorite subject is 1/4. So I'm going to come over here and I'm going to say probability of math, I'll just use M, is equal to 1/4. I need that. The probability that the student chosen is a junior. Now I'm going to say probability of junior is equal to 1/16 over 459. Next, if the probability that the student selected is a junior or chooses math as their favorite subject, so or means which one, union or intersection? Union, good. So I'm going to go probability of M or J, and I know some of these notations look weird, equals, looking 47 over 108, then we need to find the probability that you are a junior and your favorite subject is math. So I'm going to say probability of math and junior is unknown. So I'll say like X. So what you have up here are actually 3 of the 4 elements that you need for your union formula. So I'm going to write the same formula we just did on the back. So we know here that the probability of M or J is equal to the probability of M plus the probability of J minus the overlap. And the overlap would be M and J. So all I'm going to do is place numbers where they belong, and then we're going to use our calculator and get this answer. So probability of M or J is this number. I have 47 over 108. Oops, sorry, 108 equal to probability of M was 1/4. Yep. Probability of J is 1/16 over 459. And then if you would like, for simplicity, you can just replace that with like X, if you want. Now, all I'm going to do is add the fraction and then subtract it over. So what do we get from 1/4 plus 1/16 over 459? Math, enter, enter. Oh yeah, thank you. 923 over 1,836. And then minus X. All right, 47 over 108 equals that. All right, so go ahead and subtract it over. So that goes over here, and yes, I'm aware it's equal to a negative, but you're going to work that out anyways. So 47 over 108 minus 923 over 1,836. Math, enter, enter. Did we get, I'm coming over here, negative 31 over 459 equals negative X? So obviously your negative goes away, and we get the probability is 31 over 459. And right now you can leave it like that. So then it asks you, are the events the student is a junior and the student's favorite subject is math independent of each other? This is where you're going to use the rule that I had you write on the bottom of your page. So we must show that the probability the student is a junior times the probability that the student likes math is equal to these occurring together. The probability of J and M, which actually you just found. That's this one. So probability of J is 116 over 459 times M is 1/4. And is that equal to 31 over 459? I don't think they are. You guys check them yet? 116 over 459 times 1/4 is like 0.06.
29.
Okay, so no, right? Yep. So these are not equal to each other. So therefore you are going to conclude not independent. Okay, so it's not harder. It's just you're going to use an alternative rule because you don't have that two-way table. But you just have to do a little bit of multiplication. All right, let's do another one of those. And those are typically when you take a recent exam, like a 4-point question. So it does involve a substantial amount of work. So next, I'm going to advise you do the same thing and translate as you go. So the high school has a population of 1,376. Those who participate in sports. So over here, I'm going to say probability of sports equal to 649 over 1376. Probability that they like music or participate in music is equal to 433 over 1376. Then you are given the probability that they participate in either sports or music. So this is a union again. So probability of sports or music equal to 974 over 1376. What is the probability of participate in both? So we want the probability of S and M. I'm going to do the same thing. How about X for simplicity? Would you guys agree I can use the same formula as before? 3 out of 4 things? So I'm going to say the probability of S or M is equal to the probability of S plus the probability of M minus the probability that they occur together. So S and M. And then you plug in for whatever you're missing. Whatever you have, and then X is whatever's missing. So we have a 974 over 1376. Another 649 over 1376 plus 433 over 1376 minus X again. All right, so we need to add those, subtract it over, and then the negative, once again, is going to work itself out. You can't have negative probability, obviously. Math, enter every step of the way, please. And then I'm going to go 974 over 1376 minus 541 over 688, enter. Math, enter once more. Did we get 27 over 344? Yes. So 27 over 344. All right, does this one continue? Nope, that's it on that one. And that's your final answer. So that would be the probability of S and M. right, so next. You are given two events, just generic here, A and B, and determine whether or not these are independent or dependent. So I need to apply the rule. So to test for independence, I am going to go the probability of A times the probability of B must be equal to the probability of A and B. So I'm going to fill in what I have now. So this is 0.6 times 0.5. Do I know the probability of A and B? I don't. But do I know something that will help me? This. So you're going to use your rule to get this value and sub it back in. So this I'm going to find. So we're going to come off to the side here and say probability of A or B is equal to probability of A plus probability of B minus probability of A and B. Again, that is what we call the union rule. So I have 0.8 equal to 0.6 plus 0.5 minus x. So this is 1.1 minus x. Subtract that over, negative 0.3 equals negative x. Therefore, x equals 0.3. And that goes here. Actually, you know what? Are those equal? Yeah. So these are equal. I'm going to say equal. Thus, independence. So equal, thus, independent events. Okay. How's that so far? Okay with the rules? Okay. These are super easy. This is what we call the complement. The complement is the probability that something does not occur. And what you will notice is we typically use a little c as an exponent for your notation. So nice and quick. The probability it will snow is 0.26. 0.26. What is the probability that it will not snow? So if you want notation, you're going to do this. So I do 1 minus 0.26, which is equal to 0.74. That's it. Easy? Okay. So go ahead and flip them. But again, that is what we call a complement. We use 1 because probability is out of 100%. Those we talked about already. So that's just a summary of your rules. Factory produces computer chips that will be purchased by auto manufacturers. Each chip has a 1% probability of being defective. The probability of being defective is 0.01. Calculate the probability that the chip will not be defective. I'm sure you can do this without showing any work whatsoever, right? So what is the complement? You got it. That's it. Again, super quick and easy. All right, so my next. A math teacher has a box of 11 calculators and 3 are defective. So probability of being defective is equal to 3 over 11. If 2 calculators are selected with replacement, then what's the probability they are both defective? So what you're going to do is just multiply this twice. Easy. So I would do the 3 out of 11 times calculator number 2, 3 out of 11. So this would be 9 over 121. Let's get a decimal. 121 is equal to like 0.074. Okay, so pretty small. And this next one works the same type of way. You have a string of Christmas lights with 20 lights. If one light fails, the whole string goes dark. Each light has a probability of 0.02% chance of failing. So probability of failing 0.02. So therefore, the probability of not failing would be 0.98. So you probably need it anyways. So what's the probability that these will remain bright? So on this one, I had you just multiply it twice because it was short. On this one, I don't think you really want to show 20 of these, do you? No. So instead, what I can do is 0.98 raised to the 20th. Okay, just a shortcut. 0.98 raised to the 20th is like 0.668. Bump that up. All right, how are those so far? Okay. All right, we're going to start your Venn diagrams too. So we're going to do a teeny bit of coloring. So if you have highlighters or something you'd like to use, you're more than welcome. We'll just start them. They start really quick and easy. What I keep talking about is a shared outcome, and that's why we have Venn diagrams. So your shared outcomes are going to be right in the center. All right, so here is a nice Venn diagram. So it says at a high school, some students play soccer and some do not. Some students play basketball and some do not. Scenarios modeled by a Venn diagram. So circle labeled S represents students who play soccer, B is basketball. So first, we are going to color, again, nice and quick, the shaded region representing students who play soccer. How am I going to do that? Yes. Circle with the S in it. Good. Okay. Do not play soccer. What do I color? Uh-huh. Yes. Excellent. Everything else basically, right? Because it's the complement. Yep, so this is your complement of soccer. In color. Outside box 2. All right, soccer and basketball. Where does that go? In the middle. Yep. This is your intersection. So this is soccer and basketball. Intersection. How about letter D? Soccer or basketball? Actually, you do color in the part that overlaps too. Yep. No, that's okay. Yep, this is your union. It includes you combine them together. So if you think combine. So yep, this one's your union. So soccer or basketball. How about playing soccer, not soccer or basketball? Good, just the outsides. So again, it's the complement. Soccer, but not basketball. Excellent, just the S circle, not the overlap. There you go. It's just a visual way to interpret probability, and then we'll kind of solve a little bit with it down below. Okay, what you have to be aware of with the Venn diagram is you have to be aware to not count things twice. So with that being said, 230 students play soccer. That means this entire circle with an S on it needs to add up to 230. Okay? Full circle is 230. Put that here just in case you want it right now. 190 full circle play basketball. We can't do anything with those yet. Let's find something more specific. 60 students play both. Where does that number go for sure? Yes. So this is what we start with. 60. I want you to write this work down just so So again, if you look back, you know where this came from. I know full circle was 230, and now don't I know 60 of it? So what's 230 minus 60?
170.
Yep. I'm going to put that number in now. And then don't I do the same thing for basketball? Yeah, basketball is, looking for it, 190. And we already know 60 of them accounted for sure, and you can't double count people. That's 130. Next. How many students play basketball but not soccer? Just 130, right? It doesn't say probability, so it's just a number. Suppose a student is selected at random. What's the probability the student plays both sports? Yep, 60 out of 500, excellent. Let's get a decimal, and actually we need to find one more number now that I think of it, because we didn't complete this one. So 60 out of 500 is 0.12. I need this number outside here. So what I'm going to do is 500 minus 170 minus 60 minus 130. So this number is 140. And it came from 500 minus 170 minus 60 minus 130. Complete the Venn diagram by writing the probabilities in. So we're just going to divide these by 500. So 170 divided by 500 is 0.34. 60 divided by 500 is 0.12. 130 divided by 500 is 0.26. One more. 140 divided by 500 is, you got it. Okay, and I think I'll stop there. For today, we'll finish the rest tomorrow. We want to give you a chance to get started on the quick assignments. How do you feel with those probabilities so far? Pretty good? Okay. Can you please flip back to problem set number 3? I want you to practice your union rule for sure. These shouldn't take you long. Yeah, I would like you, please, to complete the front and back of problem set 3 before you return tomorrow. But I'll give you the last 10 minutes to get a jump start on that. And with your union rule, please just make sure you show that work just like we were kind of doing before. The first part you should kind of fly through. Those are just general probabilities. Again, use proper notation as you guys have been doing, and I will check those tomorrow when you come in. Figure the more homework points you get, the better. Comfortable on those? Great. But feel free to